Yesterday we had seen two types of counters, that is up counter and down counter, which was of the type asynchronous. So it was an asynchronous counter, but nevertheless it was having it could count up or it could count down. Now, sometimes in the same application, we may have to count up as well as down. We may have to count up as well as down. And in such applications, we need to have both functionalities of counting up. So if you are counting from 0 to, if you are counting 6 states, then 0, 1, 2, 3, 4 or 5. We may have to count backwards also, 5, 4, 3, 2, 1 and 0. A counter which counts m states is called as mod m counter, where m is the number of states. So if m is equal to 6, we say it is mod 6 counter. We say it is a mod 6 counter. So let us try to combine both up and down counting as far as counter is concerned. And which counter are we talking about? Asynchronous counter. So this is something that we are looking at. Okay. So please note down the question. This is like an exam problem, and everybody should really focus on this thing. Design a 3-bit up down asynchronous counter. So these are the keywords. 3-bit, whether it is a up counter or a down counter, whether it is asynchronous or synchronous. Using mode control M. Using mode control M. If M is 0, it should count up, and if M is 1, it should count down. M is 0, it should count up. If M is 1, it should count down. Here in the question, I have written use T flip-flop, but even if it is not written, even if T flip-flop is not mentioned, you have to understand that since it is a asynchronous counter, we have to use T flip-flop or shorted JK flip-flop. The shorted JK flip-flop is nothing but T flip-flop. So this is what we have to use. So please note down this question properly. Design a 3-bit up-down asynchronous counter using mode control M. If n is equal to 0, it should count up, and if n equal to 1, it should count down. So that is what we want. So let's see the solution for this problem. First, we need to decide. The word is design. The word that we are using is design. Design means we have to design from the start. So how many flip-flops should be used? How to connect them? And whether really we'll get some counting or not. That is the question. So first thing that we have to comment on is how many flip-flops. So you can see here 3-bit. 3-bit means we require 3 flip-flops. So n equal to 3, that is the number of bits, and that is also equal to the number of flip-flops. That is going to be 3. The number of states that this up-down counter can count is 2 raised to n equal to 3, that is 8. So 8 states. So it should count from 0 to 7, and it should count down from 7 to 0. So this is up counting and this is down counting. 0 to 7 is up, 7 to 0 is down. N is the number of states the counter counts, So please copy this thing. Once you do this, write done in the chat box. Yes, just a quick voice check, Karthik. Is there noise from my mic?
यस सर, थोड़ा सा है.
Okay.
सर एंड जस्ट एक पूछना था.
Yes.
सर नेक्स्ट टाइम से लेक्चर आप 10:15 से स्टार्ट करोगे क्या? क्योंकि
Why?
हम लोगों का पहले ही 9 से 10 लेक्चर रहता है.
Hmm, the department has not told me anything. We'll see that after the class. So ask the previous
सर इट
person
वाज
to end it 10 minutes early.
अच्छा, इट इज because it was mentioned in the timetable, so I thought.
No, we can ask the previous person to end it 10 minutes early because that is an unscheduled lecture. So, and this is a scheduled one. So,
हाँ ये सर. सर टाइम टेबल में भी मतलब उधर लिखा है ऑप्शनल, लेकिन सब लोग उसको ऐसे वही लेते कि शेड्यूल्ड ही है.
no,
ऑप्शनल. हाँ
you
यस सर.
you tell sir whoever it is to end it 10 minutes early because anyways in my class after every 1 hour I will be giving a 10 minutes break. So I can control things in my class, but it is not right to change everything because somebody is taking an extra class. So the person who takes the extra class should generally change it or adapt to it. So my class will start at 10, but you can tell your previous professor to end it 10 minutes early. So probably you can have a class of 50 minutes and 10 minutes of break between two classes. Okay, so let's go ahead. So here we are talking about a asynchronous counter and up down. Now you should look at this thing, this circuit. So this is a circuit that we have designed. Now what does it do? You can see, I'll just rub one. First there are three flip-flops. Clear is connected to clear terminal, preset is connected to preset terminal, and all the inputs T is connected to logic 1. Is connected to logic 1. Now if you look at these gates, I'll call them as 1, 1 and 1, and this is AND gate 2 and 2 and 2. So if you look at all the one AND gates, the AND gates on which I have written one input of the AND gate is Q. One input of the AND gate is Q. Here we have Q, and here for the second AND gate, the AND gate 2, for one of the input is Q bar. So either Q gets connected to clock or Q bar gets connected to the clock based on which of the AND gate is on. Based on which of the AND gate is on. If AND gate 1 is on, then Q will get connected to clock. If AND gate 2 is on, then Q bar will get connected to the clock of the next flip flop. And enabling and disabling these AND gates, that is AND gate 1 and AND gate 2, is done with the help of mode control. Mode control. That means if I give a 0 here, then on this line I will have 0, on this line I will have 1. So you can see the 0 line is connected to the second flip flop, and the 1 line is connected to the first AND gate, not flip flop. So the AND gate which gets a logic 1 as the other input is going to get enabled, and as a result Q gets connected to the clock through the OR gate. If I interchange this, if I make this 1 and 0, then this will become 1 and this will become 0. So this gets disabled and the second gate enables. So because of this, now the Q bar gets connected to the clock, and that is why when m is equal to 0, we get up counting. M is equal to 0, we get up counting. Why? Because Q is connected to clock, and when m is equal to 1, we get down counting because Q bar gets connected to the clock of the next flip flop. So when it is Q is connected to clock, we have up counting. Q bar connected to clock, we have down counting. So to get in more clarity on this, I will just simulate this circuit for you, and then we will have a look at other things. So it's a asynchronous up-down counter. So now you should be able to see the circuit in front of you, and the basic is all the same. So I will just run this circuit now. So initially I have to clear it and then keep clear and preset to 1. So you can see here that the counting has started. 4, then we have now 5, then we have 6, and we have 7. After 7 we get 0. So let me just, so you can copy this particular circuit, and in the meantime let me just put a small display here so that it is becoming easy for us to look at the value. So you can draw this, the schematic file of this I will just send it to you. Then if you want, you can simulate this thing at your own end later, not now. So I'm just keeping the simulation on so that you can see do this very nicely. First, I need to clear this thing. So m is 0. You can see that m is 0, and that is why it is counting up. One, then it should count to 2, so because there is a slight delay on your side, some in between only you will see 0 or something, but actually it is counting correctly. So I just stopped the simulation so that you can copy this circuit properly. So you should know that if I keep this 1, see if I make this 0, if I make this 0, then if you see AND gate number 1, if you see the top AND gates, both the input lines to the AND gate are red. That means the AND gate is enabled, and you can see the output is 1 from the upper AND gate. But the moment I make the lower AND, the moment I make this 1, you can see now that the lower AND gates got enabled and the upper AND gates got disabled. So this is what we are actually trying to do with the help of this small additional hardware of 3 gates, 2 AND and 1 OR, so that we can count up as well as down with the help of mode control. So many times we want to count up, many times we want to count down also. So please copy this circuit, and once you are done with this, just write done in the chat box. So I'm just stopping the simulation so that you can see all the values. Okay. Any doubts in this, please ask. I will wait for exactly 3 or 4 minutes, then we will move ahead. And if you just note here, we did not follow a design procedure here. Okay. So in our difference between synchronous and asynchronous counter, I told you that synchronous requires a design procedure, but asynchronous doesn't have a design procedure. So I just told you, I did not do any designing. I just told you that this circuit can work as a mode up and down counter. So whatever it is like this. That's what I just told you. I did not design it because there is no design procedure. It was just observed like this. Now, if I want a 4-bit counter, if I want to count till 15, then the number of flip-flops that I will require here is 4, because it will count from 0 to 15. So 0 to 15 is 16 states, and 16 2 raised to 4 is 16. So the number of flip-flops would be 4, n equal to 4. So in the exam, they may ask you maximum up to 4 bit. 5 and 6 bit is slightly not asked because it does not fit in your paper. But if it's like a multiple choice question, then they can ask you. If it's a 32 bit uh, asynchronous counter, how many flip flops are required? So the answer should be 32 is 2 raised to 5 is 32. So the number of flip flops will be 5. So please remember that. Once you have copied this circuit, just write done in the chat box. So how you should draw this circuit? First you draw these three boxes, that is the flip flops. Okay, then you connect clear terminal of all to one clear button, then you connect preset to preset button, and then clock has to be given only on the first flip flop, and then at the output of the first flip flop you will draw those two AND gates followed by a OR gate, and the output of the OR gate would be connected to the next clock. And you can see the T input of all the flip flops. The T input of all the flip flops is connected to logic 1. So that is the way to put T flip flop in toggle mode. That means toggle means respond only when or respond only with clock. And with clock means respond only with clock when clock changes from 1 to 0 and not 0 to 1. So response at 1 to 0 is called as negative edge trigger. So basically this is a negative edge triggered T flip flop. I have also put the PDFs of last class and last to last class in Teams. So you can just download that and keep it with you, and probably even open previous PDFs to understand what is going on in current class. So you should always have the previous PDFs when you are going for the higher classes. Now things will become complicated. So what everybody should know now is how to convert the flip flops and what are the excitation tables of each and every flip flop. That is a must. All must know that. So I had given you a summary of all the excitation tables. So I will require that today. So excitation table of every flip flop was given on one page. So just keep that thing in front of you. No need to draw that digit display, okay? You can just skip that. Just show the outputs Q0, Q1 and Q2. That's it. Because I'm using the circuit simulator, you can, these additional things can be easily added, but when you are actually drawing, it is not very easy to add this. So those of you who are doing this on a computer can also consider drawing this on DSCH itself instead of writing in your notebook. The problem is if you write in your notebook, you cannot simulate it. You have to again draw it to simulate it. Okay, Ashish has done it. Yes. Anushka, Karthik, should I wait for some more time?
Yes, sir.
Okay, I'll wait for another couple of minutes. I'm not able to drop that file there. Yeah, I can see many have done it. Okay, last 1 minute I'll just wait. And I'm just sending you the file across. Okay, so let us see the next thing in this. So this was my asynchronous counter. That is, if n equal to 1, all A gates are enabled and B gates are disabled. A is the upper gates. Therefore, uncomplemented output. So you can just write these two lines. When n equal to 0, uncomplemented output is connected as clock to the next flip-flop. This leads to upcounting, and when n equal to 1, A gates are disabled. That means upper gates are disabled. Here they are enabled. And here B gates are enabled. Here it is disabled. So complemented output gets connected as clock. write this explanation. So you can just write in short that if n is 0, up counting, if n is 1, down counting, and if n is 0, uncomplemented output is connected to next flip-flop, and if n is 1, complemented output is connected to the next flip-flop. Uncomplemented means Q. In this case, the first case, uncomplemented means Q becomes equal to clock, and in the second case, Q bar becomes equal to clock, or rather the way we write, Q bar becomes equal to, okay. So let's go to slightly different types of counters. So now we saw up, then we saw down, then we saw up down. Both the facilities are there in one counter only. But not necessarily I would always like to count from 0 to 7 or 0 to 15 or 0 to 31, that is in multiple, in the powers of 2. Somebody may say I may want to count from 0 to 6. I want to count like this. I want to count from 0 to just 5, or I want to count from 0 to 13, or the very famous one is basically the mod 10 counter, because generally we count in multiples of 10. So we may want to count only from 0 to 9. So in that case, what should we do? So now we are going to look at a special class of counters, which is the mod counters, wherein the count to which we actually count is going to be specified. So let us see that. Right. So we will directly see designs. These are all standard questions in your paper. Design mod 6 asynchronous counter using T flip-flop. Design mod 6. Mod 6. What is the meaning of mod 6? Can somebody tell me? Mod 6 means we are counting from which to which state? We are counting from which states? Just put your answers in your chat box. Mod 6 means which states are we counting?
Seven steps.
Sorry?
0 to 6, 7 steps.
0 to 6, 7 states. The answer is wrong. That is exactly why I asked you. Mod 6 means it counts 6 states. It counts 6 states. 6 states means 0, 1, 2, 3, 4, and 5. So the 6 states are this: 0, 1, 2, 3, 4, and 5. Part minus 6 to 6 is something really weird. Yes, you are right. That is going to be 0 to 5. If I say that my counter is a mod 13 counter, it's a mod 13 counter, so it should count from which to which state? Put your answers in the chat box. So you will get such questions in the IA, right? So that is going to be 0 to 12. So 0 to 12 means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 12. Correct, Asmita. So it will count 12 states. So if it is a mod 6 counter, it will count from 0 to 5. If it's a mod 10 counter, it should count from which state to which state? Mod 10 will count from
0 to 11.
wrong. It will count from 0 to 9. 0, 1, 2, up to 9.
अच्छा
So
mod
0 to
10. ओके
mod
हाँ
10 will be 10 states. Correct answer. So what now we are seeing is design mod 6 asynchronous counter. So it should count from 0 to 5. So please keep this concept in your mind. Otherwise you will do all your K-maps and truth tables wrong if you take a wrong number of states. So mod 6 means 6 states. Which are those states? 0 to 5. Mod 10 means 10 states. Which are those states? 0 to 9. Mod 13 means 13 states. Which are those states? 0 to 12. 0 is also a state. Why 0 is also a state? Because 0 represents the reset state actually. So 0 is also a state, and the state from which all systems start working is the reset state. So 0 is one of the most important states. Okay, let's go ahead. Mod 6 means I have to count 6 states. So 2 raised to 0 is 1. 2 raised to 1 is 2. 2 raised to 3, 2 raised to 2 is 4, and 2 raised to 3 is 8. So you can see we have these three options. We cannot have 0 flip-flop. So this is out of the question. So we have 2, 4 and 8. Now if you look at this 6 falls between 2 and 4. This 6 falls between 2 and 4. So the minimum number of flip-flops that we would require is 4. If this would have been mod, sorry, I did a mistake here. It's not between 2 and 4. It falls between 4 and 6. So here this is 4. So 6 falls here. So 6 falls between 4 and 8. So the minimum number of states that we have to address is 8. And to get 8, we require 3 flip-flops. So that is why m should always be less than or equal to 2 raised to n. So here m is given to us as 6. So 6 will be less than 2 raised to n only if n is 3. Only if n is 3. Now you may argue, why not 4? We need to choose minimum number of flip-flops. Why to use a flip-flop whose states we are never going to consider? We want a mod 6 counter. We don't want a mod 16 or 13 counter. So we don't require more number of 4 or 5 flip-flops. We are satisfied with the minimum number of flip-flops. So the minimum value is going to be 3, which is going to make it greater than or equal to 6. So that is why the number of states the counter counts is 6, and hence the number of flip-flops that we have to use is 3. Though this counter can count from 0 to 7, we are only going to count from 0 to 5. So actually with 3 flip-flops, we can count from 0 to 7. But we want to count only from 0 to 5. That means after 5, my system should again come back to 0. After 5, my system should again come back to 0. That is our objective. So this is what we have to actually do. Let's see how that can be done. all flip-flops are cleared. So all flip-flops need to be cleared when Q2, Q1, Q0 becomes 110. That means 110. Once you receive this, the output should become Q2, Q1, Q0 should become 000. So 6 we don't want, 7 also we don't want. So while counting from 0 to 7, we will come at 0, 1, 2, 3, 4, 5. So at 5, 6 states would be complete. So the next state of 5 should be 0. So here after 5 we should have a 0. This is what we want. So we have to stop counting. We don't want 6 and 7. So somehow we have to detect this 6, and if 6 comes, or somehow we have to detect that 5 has ended, and we need to reset back again the flip-flop. That is the objective. So when clear is 0, all the flip-flops are clear. So you can just do this. So when you are done with all this, just write done in your chat box. Then we will see the design. So again, out of these 4 counters that we have studied, at least one will come, and put a star on that up down counter. That is a very famous question in the exam. Okay, the counter that we just did before. Mod, not mod, asynchronous up down counter. So if you are done, just put done in the chat box. Okay, so let's go to the next one. So this is the circuit. Now you can see here that the T flip-flop is connected the way it is, that is Q is connected to clock. But here you can see this is Q0, this is Q1, and this is Q2. So when I told you Q0, Q1 and Q2 is 0, 1, 1, because I wrote Q1, Q0, Q1 and Q2 the other way around. Actually Q2 is the MSB, Q1 is the next bit, and then Q0. Then we have 1, 1 and 0. But in the flip-flop we are writing it in this direction. So this is Q0, Q1 and Q2. So when Q2 and Q1 are 1, and when Q0 is 0, I should reset these flip-flops. So what happens is so this is nothing but 6. So at 6, I should not go in 6, I should go directly to 0. So the moment 6 arrives, this is 0, this becomes 1, this is also 1, and this is also 1. So this is the AND gate, so the output becomes 1. And whatever this input might be, when one input of the OR is 1, here also you will get 1, and that 1 is going to reset the whole system. So that is how we actually reset at 6. Now I will show you the actual simulation of this, then you can copy. So I'm just putting this counter in front of you. Now let's simulate this thing. So you can see that initially we have to reset. So this is my reset button, and I'm resetting it. So I make it 1, I make it 0. So my counter becomes, so you can see now the counter has started counting 3, 4. Specifically at 6, you see the AND gate. All the inputs to the AND gate are 1, and that is why it resets. Now you see it will become 1, so it has reset. So at 6, everything, all inputs to the AND gate become 1, and that is why the reset signal is triggered. So I'm just stopping the simulation. So please copy this particular thing. So here please note, I have not used any uh, preset, because anyways we are not using preset, we are using only a reset. We are trying to set the system back to 0. Yes, any doubts in this? Please unmute and ask. And there are lots of gate level questions on counters. Okay, so this is going to be the fundamental for the gate exam. Around 8 questions or 9 questions will come from this part there also. Karthik, are you understanding this?
Yes, sir.
It's not very difficult, but the concept here is that since you want to count from 0 to 5, all you have to detect the invalid state and reset it. Detect the next invalid state and reset back to 0. So the NOT gate and AND gate at the top are detecting that 6, that is that invalid state, and at 6 it resets the flip flop back to 0. So it again counts back to the from 0 to 5. So once you are done with this, you can just type in the chat box mod 6 done. Anurag Bhandari, are you following this? Any doubts?
Yes, sir. Means no doubts.
Okay. Pragati, are you following this? So again, it is my suggestion, those who do not have laptop or desktop, please consider buying one. Okay? Mobile is not the right way of learning a class. There are many limitations, though you can, but there are many limitations. Typically speaking, you should have two screens. On one screen, you should be simulating the things on the simulator at your end, and on the second screen, you should be viewing my PPTs. So on one screen, you should view the PPT. On the second screen, you should do the actual simulations. So that is how it should actually work. That is why I insist on dual screens. And a screen is much cheaper than a phone. I hope you know that. Okay, any doubts in this? So in this particular circuit, I have used a T flip-flop. I have used a T flip-flop in which there is a D register. So this T flip-flop is actually a flip-flop with a D flip-flop inside. And now why I have done it? Because I also tried for a long time. Here, the reset signal, if you connect it to a clear pin, then the problem happens here is that you cannot reset it because it is already connected to a fixed value pin. So the wire which is connected from the OR gate to the reset terminal of all the flip-flops, this wire should be controlled by the output of the OR gate. This wire should be controlled by the output of the OR gate. If you connect a button there, then the value on that line gets controlled with the help of that button, not the flip-flop. So we want this value to be variable and the control should be with the OR gate. So that is the reason why I am going for a T flip-flop with a reset terminal and not a preset one. So if you try to do it with the earlier flip-flop, which is having preset and clear terminals, this circuit, the same circuit will not work. Okay, so you can try it at your own end, but it doesn't work. Okay, have you completed this diagram? Again, just simple three flip-flops. Q is connected to clock, and you can see that Q0, Q1, Q2, they are taken at the top. So that, so here we can have a, you can see here one alphabet thing. So you can put text here if you want. You can put Q0. Then if you want text here, So here we can put Q1. Then here we can put Q2. The moment Q0, Q1 and Q2 are 0, 1, 1, the counter resets. Okay, Deepak, very good. Very good, Deepak. So there is a problem with this flip-flop actually, that the counter goes, though it is counting from 0 to 5, it goes in the sixth state, that is the invalid state, for a certain time. Though it is not for complete time, but it goes in that state for a certain amount of time. Unless it goes in that state, the output cannot become 1 for the AND gate. And that is why this creates a certain problem called as a glitch. This creates a certain problem called as a glitch. So let us look at that problem. So here, this is my T flip-flop, as in our diagram, the same one, exactly the same. So this is the timing diagram of the flip-flop. Now, I would want you to draw this timing diagram, because this is very peculiar timing diagram. So you can see here, in the exam also, you will have to draw the timing diagram. You will have to draw the timing diagram. So what is the technique to draw this timing diagram? The technique is, first you draw the clock signal, and draw the clock signal as small as possible. That means the width of this should be as small as possible, so that you can fit so many states inside this. So let's say this is in this fashion. So here, this is the negative edge, or we'll say the falling edge, when the output becomes from 1 to 0. So you can see at the falling edge, Q0 changes. At the rising edge, there is no change in Q0 or Q1 or Q2, or even if it's Q3, it is not there. So only at the falling edge. So this is my first clock. So this is my 0, 1, 2, 3, 4, 5. So 5 clocks, I get 5 outputs, still 5. At the sixth clock, my output becomes 0, then again it becomes 1. At the 8th clock, it again becomes 2. So actually, how the counter is counting: 0, 1, 2, 3, 4, 5. After 5, it again counts 0, 1, 2. So please draw this timing diagram, or will you draw it later? I think you can take a print of this and keep it with you. No need to draw this diagram. So it is 11 o'clock. So we will take a 10 minutes break, and I will leave this diagram on your screen, so we will see this after. So we will resume back at 11:10. In the meantime, if there are any doubts, you can ask.
फिर भी रुक 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 रुक
Yes. Somebody wants to say something? Okay, so it is 11:10. So let's move ahead. Okay. Now you will design on your own a mod 16 asynchronous counter. Now first of all, you tell me mod 16 means it will count from which state to which state?
0 to
Or
15.
0 to 15. That is right. So it will count from 0 to 15. How many flip-flops will be required?
4.
That is right. So 4 flip-flops will be required. So M is 16. So number of flip-flops will be 4, where M is the number of states of the counter. And this is going to be the circuit. So you can see what is different in this circuit than the up counter circuit is just this additional flip-flop. This additional flip-flop, that is extra, that's it. So all the preset terminals are shorted and connected to one pin, and their clear terminals are also shorted and connected to one pin. Then the Q is given as clock to the next circuit, and that's it. So this is my mod 16 counter. So here you can see there is one additional Q3. So it can count up from 0, 0, 0, 0 to 1, 1, 1. So that is 0 to 50. So I'll just show you the simulation of this thing. Anusha, there is lot of noise from your microphone. Please mute. So this is the circuit. Now I have to first clear it, and now let's see whether this thing simulates or not. Okay, there is a small problem inside this. Just solve it. I'm just clearing it. So you can see it starts from 0. So when you look at the output, you should look at the LEDs and the display. Look at the LED and the display. So if it shows 10, it should show 8. If it shows something else, it should show that particular number. So this will count like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it will count it as ABC. So A is 10 basically. So please copy this circuit. Once you are copying this circuit, done, just write done in the chat box. It is exactly similar to the previous one with the additional P flip flop. Once you are done, just write done in the chat box, please. Tanish, Are you following this?
Yes, sir.
What about Pranjali? Are you following this? When Pranjali is not there. Rohit Sawant, are you there? Yesterday I could not hear you. Rohit, are you there? Rohit, I can't hear you. Sorry. Now I can hear you in little bit. So you are following, na?
Yes, sir.
Ruchira, what about you? Is Ruchira there? Okay, yes, she is the first one to solve this. Very good. Okay. That is correct. That is correct. So you have implemented yes shift using D flip flops, right?
Yes, sir.
So with D flip flop, it will always be a better performance. Okay, so I'll wait for another 2-3 minutes so that we can complete this. Or should I go ahead? It is just one flip flop extra. That's it. So I've just put this file here for you so that if you want to simulate this at your own end, you can. Okay, Shubham, let me check. Okay, good. Suman, very good. So those who are not able to like make this quickly, I have just put a that schematic file there. You can see that asynchronous something. You can just open it and check for yourself whether this thing works properly or not. Okay. So let's go to the next counter. So this is the timing diagram for the counter. So you can see the timing diagram for this counter is comparatively huge. So there are going to be 16 states, and the states are going to be from. So this is your MSB and this is your LSB. So you have to read like this. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15. And then again here you are having a 0, 1. So it counts from.
Hello, sir. You are on mute.
Yes. Can you hear me now?
Yes, sir.
Yes,
Yes,
sir.
sir.
So my teams had, I think, gone bad. Okay, yes. So let's switch back. So now you will design a mod 10 or a decade counter.
Sir,
Decade
screen
means,
is not visible.
yeah. So you will now design a mod 10 or a decade asynchronous counter using a T flip-flop. Asynchronous is understood that has to be a T flip-flop, and decade means obviously m will be equal to 10. So now your counter will count from which state to which state? Please put your answers in the chat box.
0 to 9.
Yes, it will be from 0 to 9. That is right. And how many flip-flops will you require?
4.
By 4.
10 is less than or is less than 16.
Yeah, so with one flip-flop, 2 raised to 1 is 2. Then 2 raised to 2 is 4. 2 raised to 3 is 8. And 2 raised to 4 is 16. So 10 falls here between 8 and 16. So you will choose the maximum one. And here we have 4. So that is why n will be equal to 4. So n equal to 4 satisfies this particular condition. Hence the number of flip-flops is 4. So note, all flip-flops will have to be reset when this. So you have to detect 1, 0, 1 and 0 and give it to a AND gate. So wherever there is a 0, you will put a NOT gate and all that will go into this, and this will go to the clear terminal. This will go to the clear terminal. Correct. Omkar 4 flip-flops, Ashwin, Ashish, Hemant, Karthik, Tanvi, all are right. Good. So start implementing this flip-flop. Now here with 4 flip-flops, we are equal to 0, all the flip-flops get clear. So this is the logic for that. We have all 4 flip-flops here. Now this is Q0, this is Q1, this is Q2 and Q3. So when this is Q3 is 1, 0, 1, 0, my flip-flop should reset. Now you can see, I told you that you can use a NOT gate, but NOT gate only negates. So instead of using an inverter, instead of connecting it to Q, here I have connected it to Q bar, here I have connected it to Q, here again I have connected it to Q bar, and here I have connected it to. So if I would connect it to Q, then I have to use one NOT gate. So and NOT gate is simply negating. So why unnecessarily use that gate? Directly use the Q bar, the other output which is already there with us. So when this is the case, that time all these outputs will be 1, 1, 1, 1, and this is permanently connected to logic 1 because we have a 5 input gate in DSH. So this is like a 4 input AND gate, 1, 2, 3, 4, and the outputs here are going to be Q0 bar, Q1, Q2 bar, Q3, and here we will get the output. So this is the slight hardware that you have to design. If you are drawing it in your notebook, then you can show this gate directly for input. If you are drawing it on DSCH, then you have to make this S is A and B and C and D and D, because by default in DSCH it will be A or B or C or D or E. It will be a OR logic. So you have to double click on it and make it to AND. So I am showing you the simulation now. So we have a synchronous mod 10 counter. So again you reset, it becomes 0 and the counter starts counting. Let's see whether it counts from 0 to 9 and then resets to 0 again. Yes, it has resetted to 0. So if you are not able to see all the lines on the screen, I'll make the background white. Is white background better or black for you? I will keep that background. So please draw this circuit. And just note, wherever there is a 0, I have connected it to Q bar. Wherever there was a 1, I connected it to Q. In mod 6 also we could have done that, but I just wanted to say that either you put a NOT gate or you can directly connect it to. So in case you want to see the pins and their states, so you can see the values at each and every pin, how the pin values are changing. So once you are done, just say done in the chat box. And have habit of using simulator. Okay, engineers should always use simulator. Pen and paperwork is okay, but what you are designing, you should implement and see. After 9 it becomes 0. Yes. So it is perfectly working like a mod 10 counter. Now let's see one small problem is here you can see that after 9 what should come is 0. After 9 what should come is a 0. After 9 what should come is a 0. So let me just expand this and show you this problem. This problem is called as glitch problem. You can see here after 9 we want a 0. So after here we should have 1 0 0 1, or Q3 should be 1, Q2 should be 0. I want 0 0 0. After 9 I want, after 1 0 0 1 I want 0 0 0. But you can see here that there is a problem here. So if you look at this particular area, this and this extending for some time delay, this is called as glitch. This is called as glitch problem. It goes into an unwanted state for some time. So this is 1 0 0 1. Here we have 0 0 0 0. But here in this position, here it is something else only. It is 1 0 1 0. So you can see that 9 becomes 0, but for a very small time it is 1 0 1 0. That means for a very small time it goes into the 10 state. It goes into the 10 state. So this is the problem of this counter, that it goes in an unwanted state for a very small time and causes something called as a glitch. This is the glitch. This is called as the glitch problem. Anyways, so you can start copying it. Okay, Suman, perfect. Very good. So I want you all to do this on simulators only. Yes, correct, Shubham. Shubham, I think it becomes very easy when you want to add something, right? So the drawing part becomes faster on the simulator when the circuits are slightly similar later on. Okay, anyways, I'll wait for another 2 minutes until you draw this. So here we have Q bar, Q bar. So those who have completed this, you can consider drawing the timing diagram. Okay. So let's go ahead with the timing diagram. Again, you can see that it is counting from 1 to 10. This is at the falling edge. At the falling edge, we are getting everything. So this is my 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then here you can see it is again 0, 0, 0, 0. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, and then again 9, and again it will become 0. So basically the counting is from 0 to 9, and then again it's resets. So if you actually draw the circuit diagram and simulate, this timing diagram you will directly get from the simulator itself. You don't have to do any other additional effort to do it. So let's look at the glitch problem. The glitch problem in a synchronous counter. So just now I showed you a counter. We saw mod 10 actually. So if you consider like a mod 7 counter, which counts from 0 to 6, and the invalid state is 7. So the valid states are from 0 to 6 for a mod 7 counter. However, the counter enters the 7th state for a small duration of time. For a small duration of time. Due to this, unwanted pulses will be present at the output. So just now I showed you the unwanted pulses. These unwanted pulses are called as glitch. These unwanted pulses are called as glitch. Mod 7, n is 7. N is the number of states the counter can count. So here n is less than 2 raised to n and 7 less than 2 raised to 3. So the number of flip-flops that again we'll be using is 3 only. So this is the same thing that we will get, but if you look at the timing diagram, you will see such pulses. So for some time it enters 7. Actually this is 6 and this is 0. This 7 is not desired because for a mod 6 counter, it should count from, sorry, mod 7 counter, it should count from 0 to 6. 7 is invalid, and then again it should start counting from 0. But for a small duration of time, it can be equal to half the clock. It can be t by 2. It can be anything, t by 8, t by 16, t by 10, whatever. It is for a small duration of the clock that it enters the 7th state and then it becomes 0. So actually it should count from 0, 1, 2, 3, 4, 5, 6, and it should go to 0. But because of this glitch problem, you get that 7 for some time there. You get a 7 here for very small time, and that is called as glitch. So for that much amount of time, your outputs are bearing a wrong value. So I'm just going back. So you can just write point number 1, 2, and so I am asking you some questions now. For a mod 6 counter, which are the invalid states? For a mod 6 counter, which are the invalid states? Type your answer in the chat box. For a mod 6 counter, which state is the invalid state? Anusha, only 6? It should be 6 and 7. Both 6 and 7 are invalid state. You should ask a question to yourself like this. When sir is asking mod 6 counter, means which sir is asking for invalid states. But what is the valid states? Valid states are from 0, 1, 2, 3, 4, and 5. So the invalid states will be 6 and 7. Vishwas, it should be 6 and 7. Hemant, 6 is not the only invalid state. Both 6 and 7 are invalid. Shubham, it is not just 7. It will be 6 and 7.
सर हाउ 7 also मतलब 6 तो पक्का है 7 कैसे मतलब
See, mod 6 counter means it should count from how many flip-flops will you require? 3.
yes sir हाँ
With 3 you can count from what? 0
2
to
5
7.
अच्छा हाँ हाँ yes sir
The mod 6 count from what? 0 to 5.
5 okay अच्छा
So which are the invalid states? 6 and 7.
7 okay
It is not just 6, it is not just 7. Both 6 and 7 are invalid. Yes, Deepak, Anusha, Asmita, Ashish, Shubham, okay.
so sir in mod 10 counter
Hmm.
invalid state would be 10 11 12 13 14 and 15 right
Right.
okay got that
Because
answer
mod 10 counter, every one of you, see, Vishwas has asked given of another example. Mod 10 counts from 0 to 9. But to count to 0 to 9, I require 4 flip-flops. And with 4 flip-flops, maximum I can count up to 15. That is 1, 1, 1, 1. So I am counting only after till 9. So automatically 10, 11, 12, 13, 14, and 15. So 6 states are invalid states. Okay, again I am asking a question. For mod 29 counter, which are the invalid states?
Twenty-nine, 30, 31, 32.
32 is wrong.
29 30 and 31
This counter will count only up to 31. Mod 32 means it will count up to from 0 to 31. Yes, did you get it?
Yes, sir.
purposely I am asking you these questions. Mod 32. I said mod 29, na? But to implement mod 29, we require 5 flip-flops. Now 5 flip-flops means you can count from 0 to 31. You are counting from 0 to 29. So 30 and 31 become the invalid states. Okay, another example. If I want to make a mod 1000 counter, which are the invalid states? Sorry, this is 0 to 28, not 29. So here we will also have 29. So Deepak, yes, it is not 29 to 32, it is 29 to 31. Deepak right, Sumant is also right, Asmita is also right, Hemant is also right. Yes. Tell me, which are the invalid states for a mod 1000 counter? Okay, right. Because mod 1000 will count from 0 to 1023. So how many flip-flops will be there in this? How many flip-flops?
10.
10. Why? Because 1024 is 2 raised to 10. So you will have 10 flip-flops. So it can count up to maximum 0 to 1023. But I am counting from 0 to 999. So my invalid states will be from 1000 to 1023. So there are 24 invalid states. So I hope you are understanding this thing very clearly. Okay. So please draw this timing diagram and just show how I have shown the glitch there. So to solve this glitch problem, we are moving our focus to synchronous counter. To solve the glitch problem, we are now changing our focus to synchronous counters.
So for this glitch one, we don't have to draw that circuit, na? It's
No,
understood means.
no, not required. It is just for your information.
Okay, sir.
Glitch you can show in timing diagram, na? So timing diagram is important.
Yes, sir.
Circuit is okay, it will count only, na? Whatever it is, it will count. Okay, it's 12 o'clock. So it's time for the second 10 minutes break. So we will resume back at 12:10. If there are any questions, I am here to take it.
Hello, sir. Sir.
Okay, so let us resume back. Just give me an audio check, somebody, please.
Yes, sir.
Yes, audible.
We don't want this inverse slide. So the solution to the glitch problem is the use of synchronous counter. Okay, the solution to solve the glitch problem is use synchronous counter. We want very smooth counting. We don't want even for some time the output should go in an unwanted shape. So that is the reason why we use synchronous. And there are many other advantages. So those 13 points I have already told you. But synchronous, we can remove glitch. We can remove glitch. But this counter can face another problem called as lockout. But we can solve even that. So our discussion is to remove the glitch. Synchronous operation itself is sufficient, but it introduces another problem called as lockout. So let us see the design steps for the synchronous counter. I told you that asynchronous counter do not have any design steps. I was just showing you the diagram and you are implementing it in the simulator. But synchronous counters will have design steps. So please write down these design steps. They are extremely important. First, calculate the number of flip-flops. So that is slightly easy to do because if it's a mod 6 counter, now I think everybody has got the knack of identifying how many flip-flops are to be used. Then step number 2, write the excitation table, calculate the number of flip-flops. Step number 3 would be, you would be calculating the truth table. Step number 4 would be, you would calculate the equation for inputs of the flip-flop used. For example, if you are using a D flip-flop, so you will have D in terms of Q3, Q2, Q1, Q0. Will be a function of all these outputs. Then fifth step would be implement the equations that we did in step number 4. So calculation of equation will involve K-map, because we can derive Boolean expressions using K-map, and then finally draw the state diagram. So just copy this thing. Once you have copied this, just write design steps done. Design switch is not switch. I think it is design steps, right? I think there is a typing error. Okay, I'll wait for another 1 minute just for you to copy it. So step number 1 and 2 are pretty simple. 3 is you have to apply your brain, and 4 is you have to apply your K-map skills. So 3 and 4 are crucial. 3 and 4 steps are crucial steps. This is where you have to think. In step number 2 and 3 and 4, you have to think. Okay. Okay, so let's see a design directly, which will be based on these 6 steps. So the first design is design a 3-bit up counter. Design a 3-bit up counter using JK flip-flop. Now synchronous counter can be designed using any flip-flop, D, T, JK, SR, any flip-flop. But mostly they will give you D, T or JK, and out of this also they will preferably give you a D flip. But here we are going to do it using JK flip-flop. So right, solution to this problem, step number 1, calculation of number of flip-flops. So 3-bit means straight away my n is 3, and if n is 3, then the number of states that it can count is 8. Can you tell me which are the valid states? Which are the valid states for this flip-flop? Yes, which are the valid states for this flip-flop? 0 to 7. Okay, Hemant.
0.
Anybody else? So that is right. Hemant is right, because here we have not specified mod 6 or mod any mod value. So in that case, the maximum value that the counter counts becomes the value for the counter. So here it is going to count from 0 to 7. Right. Next, step number 2. Step number 2. That is the excitation table for the given flip-flop. Excitation table for the given flip-flop. So which is the given flip-flop? JK. So I am writing the excitation table of the JK flip-flop. So this is your present state. This is your next state. So excitation table is always in terms of input in terms of outputs. So both of these are outputs and these are your inputs. And the first one is the present state, the second one is the next state. So you might be in state 0. Your next state can be the same state or it can be 1. You might be currently in state 1. Qn can be 1, but the next state could be 0 or 1. And for that, these J and K we have already derived. This excitation table we have already derived. So when Qn and Qn plus 1 is 0, 0, J is 0, K is don't care. For 0, 1 it is 1 don't care. For 1, 0 it is don't care and 1. And for 1, 1 it is don't care and 0. So once you write this excitation table, write ET done. Write ET done. So I want each one of you to copy this one example. Okay, this is a example for the design. Step number 1 was simple. Step number 2 is remembering the excitation table, but don't worry, over a period of time it will sink inside you. Okay, Anusha, what about others? Okay, so just write roughly Qn plus 1. I think just 4 columns should not take much time to write. Now let us go to step number 3. So step number 3 was making the truth table. So since there are 3 outputs, n is equal to 3, there will be 3 present states and there will be 3 next states. So Q2 plus, I am writing this Q2 plus is the next state of Q2. Q1 plus is the next state of Q1. Q0 plus is the next state of Q0. So now what I will do is I will see what is this combination 0 and 0. For that, J2 is going to be 0. J2 is going to be don't care. Mute your mic. Yeah. So K2 is going to be don't care. Similarly, for the next one, you can see here this and this combination is the same. So Again we write 0 don't care, 0 don't care. Here we have 0 1. So if you look in the excitation table, J2 K2 will be 1 and don't care. Then for these three values, 1 and 1, my J2 and K2 are going to be don't care and 0. And again for 1 and 0, it is going to be don't care and 1. So basically what you can see here is that I wrote J2 and K2 in terms of Q2 and Q2 plus. I wrote J2 and Q2 in terms of Q2 and Q2 plus. Similarly, I will write J1 and K1 in terms of Q1 and Q1 and Q1 plus. So Q1 and Q1 plus, and J0 and K0 I will write it in terms of Q0 and Q0 plus. So this will give me J0 and K. So please note this excitation table, and Q1 I will write it in terms of Q1. So that will give me J1 and Q1. Yes, any doubts in this, please ask. So once you write this, you can write step 3 done. So basically I want now input as a function of Q and Q plus. So there are 6 inputs, J2, K2, J1, K1, J0, K0. So I will require 6 K maps, and there are 8 terms. So J2 depends on Q2, Q1, Q0. So there are 3 variables. So I will require a 3 variable K map which will have 8 cells. So first you copy this, and if there is a doubt here, please ask. For how to write the next states of Q2, Q1 and Q0. Yeah, so Q2, you can see here, so that's a good question. Okay, I'll answer that. Now, let's say this counter is counting from 0 to 7. So that is 0, then 1, then 2, then 3, then 4, then 5, then 6, and then 7. So let's say that my present state is 0, 0, 0. My present state is 0, 0, 0. So currently I am in 0, 1, 2, 3, 4, 5, 6, and 7. So the next state of 0, after 0, what do you want? You want 1, right? The next state of 0 is 1. So if this is 0, 0, 0, the next state has to be 1. If currently I am in state 1, my next state has to be 2. If currently I am in state 2, my next state has to be 3. If currently I am in state 3, my next state has to be 4, 5, 6, and 7. So if I am in 6, my next state has to be 1, 1, 1. But if I am in 7, after 7, again it should come back to 0. That is why my next state is here 0. So based on present state and next state, we can generate the excitation table for the flip-flop. Anusha, have I answered your question? So if I am in present state 0, my next state would be 1. So present state 0 means it is 0, 0, 0. Next state will be 0, 0, 1. If my present state is 1, that is 0, 0, 1. My next state should be 2, that is going to be 0, 1, 0. So actually, if I'm putting a demarcation line here, so if this thing is 1, this thing is going to be 2. So the next state of 1 should be 2, the next state of 3 should be 4, the next state of 4 should be 5. But what should be the next state of 7? 7, the next state cannot be 8 because 8 would require one additional bit. So it should again return back to the original state. After 7, it should again return back to 0. Yes, please clear your doubts about this table. Any doubts? You can unmute and ask. So once you are done drawing this, right? Step 3 done. Understand and write. Keep the excitation table, that is the previous one, of the JK flip-flop in front of you. Okay. What about others? Okay, Deepak. Karthik, should I go ahead or should I wait?
Yes, sir, we can go ahead.
Sir,
Yeah.
sir, can you please explain the once more again for inputs for flip flop? I didn't get that how don't care and zero are coming.
Yeah. So for that, I'll go to the previous slide. So what you do is you keep the JK flip-flop excitation table in front of you. with Qn and Qn plus 1.
Yes, sir.
Yeah. So now if you see here, I am looking at this Q2 column and Q2 plus column. Okay.
Okay, okay, sir. Huh.
Now in that Qn is 0, Qn plus 1 is also 0. So what is there in the excitation table for 0, 0?
For J and K, right?
Yes.
Zero and don't care.
So that is why I wrote 0 and don't care. Now you can see the
Okay.
next three conditions are also same. So I wrote 0 and don't care. But now if you go here to this condition, you can see it is 0 and 1, right? So what is there in the excitation table?
Zero and one. One and don't care.
So that's why I wrote 1 and don't care.
Okay, huh. Huh.
For the next three, for 1 1, it is don't care and 0. And for 1 0, it is don't care and 1.
Okay. Okay,
So
अच्छा.
that is why step number 2 is important, because without writing step number 2, you cannot fill this table.
Yes, sir. Okay, okay, okay.
So that is why step number 1 is number of flip-flops. So number of flip-flops gives you an idea of the number of inputs and outputs. Then step number 2 is the information about the flip-flop that you are going to use. In this case, it is JK. So we will write excitation table of JK. With the help of this excitation table, I will fill this step table in step number 3.
Okay, yes, sir. Got it. Okay. Thank you, sir.
Yeah. Yes, please ask doubts. Those who have understood, fine, but doubt asking is important. Okay, so let us go ahead. Now, to do step number 3, step 2 was important. That is, your excitation table had to be in the front. Now, excitation table, even if it's not there, it's fine. But this entire truth table has to be in front of you. Or we should actually call this also as excitation table, because it is a combined excitation table for all the three flip-flops. It's a combined excitation table for all the three flip-flops. So this excitation table should be there in front of you. Now, first will calculate J2. First we will calculate J2 in terms of Q2, Q1, Q0. Then we will calculate K2 in terms of Q2, Q1 and Q0. And then J1, K1 and J0, K0 in terms of the present states. These inputs do not depend on the next state. The current inputs will depend on the current state only. It will not depend on the next state. Okay. So I'm just going ahead. Step number 4. Calculate the equation for inputs of flip-flop in terms of present input states. So there were 3 flip-flops. So we have to find out J2, K2. Then we have J1, K1. Then we have J0, K0 in terms of Q2, Q1 and Q0. So in terms of Q2, Q1 and Q0. So now first is calculation of Kmap for J2. So this is my Kmap. So you can now tell me at which places this is going to be 1 and at which places it is going to be 0. So fill this Kmap. So you can see at 0 position we have 0, 1 and 2. We are having 0. At 3 we are having 1. And then 4, 5, 6, 7 are don't care. 4, 5, 6, 7 are don't care. So my K-map becomes like this. So you can see that there is just one pair. And can you tell me the term here? What is this term in terms of Q2, Q1 and Q0?
Q1
Q1,
Q0.
So that will be Q1 and Q0. So J2 is going to be Q1 and Q0. Don't write this, write only the second K-map. The first one is for me. That is right, Shubham. Q1 and Q0. J2 is going to be Q1 and Q0. Similarly, can you, those who have completed this K-map, can you go for K2? And you can write the expression for K2 also in the chat box. K2 is equal to what? So for K2, 0, 1, 2, 3 is don't care. And then 4, 5, 6 is 0. And 7 is 1. And 7 is 1. So you just write for J2, this is the K-map. Now for K2, first 3, 4 are don't cares. Then 4, 5, 6 is 0, 0, 0, and 7 is 1. So again you will get a pair in the same position. Again I'll get a pair in the same position. So what is K2? K2 is again the same. It is Q1 and Q0. That is right after it. K2 is same as J2. K2 is same as J2. Now I want you to calculate for J1, K1, J0 and Q0. Come on, do it. Those who are copying for K2 can copy. Okay. So let's go to J1. So for J1, we have, this is 1. Then we have don't care, and then we have, this is 1, and then we have again don't care and don't care. So you can see that we will have a quad. And what will be the value of this? J1 and K1 both are Q0. Correct or correct? Good. Go for J0 and K0. Okay, Hemant. That is correct, Hemant. So the value here is Q0 and J1 is equal to Q0. So only draw the second K-map. I am repeating again and again. And just write this. Just write the K-map and write this. That's write the K-map and write. No need to write all these other things on the slide. Yes, correct.
Sir, and Also, there is no need to write that 0 also, na? In the
There
second
is,
KMF.
yes, there is no need, but I just wrote it somehow. I don't know
Okay,
why.
okay, okay, sir.
When you don't write anything, it means it is a 0. Okay, Asmita, can you go ahead with J0 and K0? So let's see the calculation of J0. Sorry, K0, K1 first. So K1 will be looking like this. Where you have don't care 1. So this is the quad that we will have. This is Q0. K1 is also there. Tell me J0 and K0. Okay, let's go to J0. So J0 will be 1, don't care 1. And then again we have 1, don't care. Sorry. It's 1, don't care 1, don't care 1, don't care 1, don't care. So the Kmax will be something like this. So what will be J0 now? So we will get a quad. No? So what will be the value of J0?
One.
Yes, that is right. So when J0 is not dependent on any of the variables, J0 will be, this represents just 1. So J0 is 1. So Suman, you are right. J0 and both K0 is also 1. But just see for the positions of those ones and don't. Yes, yes, correct. So I'm just going to K0 now. For K0, our positions are like this. Don't care 1, don't care 1, don't care 1, don't care 1. So again we have these positions and 8 of them together. So even that is going to be 1. Okay. Now read step number 5 in the design step. Read step number 5. Implement this thing using the flip-flop. Implement the equations using the flip-flops. So first you draw 3 JK flip-flops, one after the another. First you draw 3 JK flip-flops, one after the another. So let's go ahead and see how the implementation is. So now here we have 3 JK flip-flops. You can see here that here J and K. First of all, in all the 3 cases, J2 is equal to K2, J1 is equal to K1, and J0 is equal to K0. That is why whatever their value is, first I have shorted J and K. First I have shorted J and K. Then what I have done here is that you can see this is my Q0, this is my Q1, and this is my Q2. So this is JK flip-flop number 0, 1, and 2. So for Q0 or J0 and K0 is permanently connected to 1. So this is my logic 1. For J and K, for the second flip-flop, that is J1 and K1, this is J0 and K0 is always equal to 1. J1 and K1 is equal to Q0. So that is why this Q0 I have connected it to J1 and K1. Then for this J2 and K2, this has to be Q1 and this has to be Q0. So what I will get here is Q1 and Q0. So I have used the AND gate to take Q1 from here and Q0 from the previous state to get Q1, Q0 as J2. So J2, K2 is Q1 and Q0. So now let us simulate this circuit for even better understanding. Okay. So this is the same circuit and we can simulate it here. So first you have to clear and reset it to 1. So now we have 0. If you want, we can also have that display for our own convenience. Here and let's connect this thing. Okay, so like this. So let's say 0. It should come from 0 to 7 and you can see that it counts perfectly. Our design should work. See, two LEDs are growing. Then we have now 4, that is 100. Then we have 5, 101. Then we have 6, 110. And then finally we have 7, 111. After 7, it should now become 0. See, now then 0. Yes, so perfect. Our design is perfect. There is no flaw inside it. So you can use this design to implement the counter. So you saw just now that this particular counter involves a design. Also, you can see all flip-flops are clocked together. That means there is a common clock which goes to all the flip-flops. So all flip-flops are clocked at the same time. Now, is there any performance improvement? Let us check. So you can see that here very clearly that especially when there is a change from 7 to 1, you can see when there is a change from 7 to 1, here there are no unwanted states. After 7 there is directly 0 0 0. After 7 there is directly 0 0 0. So the glitch problem gets solved. It doesn't go into the 8th state. So the glitch problem gets solved. Okay, copy this diagram. So this is the next thing that you have to draw. This is our step number 5. That is the diagram of the implementation. So I'll just come back to this diagram. Let me show you the next part. So this is our diagram. It is the same that I saw you just now. Just now we simulated this thing. And step number 5 was implementation of this diagram. And step number 6 is the state diagram. Step number 6 is called as the state diagram. So how will you draw the state diagram? You will just write 0, 1, 2, 3, 4, 5, 6, 7. But after 7, you should show an arrow back to 0. So this is crucial. Here there is increment by 1, 1, 1. This is plus 1, plus 1, plus 1, plus 1, plus 1. But here, this is not a plus 1. This is actually a reset. So 7 to 0 is basically a reset. So I'm going back to the diagram. Please copy this diagram. Yes, any doubts in this? Please ask. So this is flip-flop number 0, 1, and this is J0, J0, J1, J1. Yes. When this step 5 is done, write step 5 done in the chat box. Okay, Gaurav. Okay, step 5 is done. Okay, now you take down this state diagram 6. That is very simple. Just you have to draw 4, 5 blocks and show some circles and join them. But please understand the meaning of them. From 0 to 7, it's an increment operation. But from 7 to 0 is a reset operation. 7 to 0 is a reset operation. So this question has come at least 3 times in the exam for 10 marks. So that is why I thought I should do this question with you. So that is step 1 to step 6. Step number 1 is identify the number of flip-flops. Step number 2 is determine the excitation table of the flip-flop that is being used. Then you make the combined excitation table. Then you implement or determine the equations for the input using K-map. And then you do the actual implementation in step number 5. And step number 6 would be the state diagram, which represents what this counter actually does. So this represents what this counter actually does. Yeah, so it's 1 o'clock and that's it from my side for today. Next time we will start with more melee kind of circuits. So I want you to do this excitation table part thoroughly. Keep the by heart that excitation table for all the flip-flops. Nothing else is required, but yes, excitation table you should know. So how you should know the truth table of the gates. Similarly, you should know the excitation table of the flip-flops. Then only you can do some kind of design. Okay, so I have taken the attendance. So that's it. If there are any doubts, I'm here for another 5 minutes. Otherwise, you can log off. Thank you.